It gives me great pleasure to introduce today's speaker. This is Matt Pyle. Matt received his PhD at Stanford under the supervision of Blas Cabrera. He then came here to Berkeley as a postdoc in the Satterlee group. He was then appointed as an assistant professor in the physics department, where he is still today, as you can see. And he has his research focused on experimental studies of dark matter. And for the work that he's done, he received the Henry Primakoff Award, and I want to read the citation, for developing high-resolution, ultra-low threshold cryogenic detectors which have defined new directions for research and development and opened possibilities for probing dark matter particle masses previously considered inaccessible. So it gives me great pleasure to introduce Matt. Take it away.
Thanks so much, Chris. So thanks for having me. So let's start with some observational evidence for dark matter, and we'll just go through a quick review. So first comes first, we have galaxies. And if we observe their velocities of stars as a function of radius, what we find is that stars at very high radius are traveling faster than we would naively expect if all of the mass was at the core of the galaxy. So this suggests that there is dark matter, matter we can't see out here at high radius, that pulls those stars around the center. We also see that with Big Bang nucleosynthesis here, which I'll talk about a little bit more in detail in a second, we see that the dark matter must be non-baryonic, and only something like 5% of the energy of the universe is in baryons. So we're in the age of precision cosmology with CMB, and where we can measure various quantities to the 0.1% level. And you see that over here that this is really like given us a very powerful view of what the universe is made of. And it's something like, again, 25% dark matter, 5% baryons, the stuff we're made out of, and 70% dark energy. So why do we care so much about searching for dark matter? Well, the first thing is it's just 25% of the universe by mass, by energy. So that makes it pretty important. But more importantly, it is the one particle we know outside of the standard model. So, and because of this, the hope is that by playing with it, by interacting with it, by understanding its mass, its charge, its spin, how it couples to the visible sector, how it's generated, it'll give us insight into the laws of high energy physics at scales that are currently inaccessible to us. So for the past 35 years, there has been a huge experimental focus on weakly interactive massive particle theories. And there's a good reason why. So the reason is that these basic theories say that we start with dark matter that's in thermal equilibrium in the early universe when it's very hot and particles are annihilating and creating each other all the time. And then as the universe cools and expands and the temperature of the universe goes below the temperature of the mass, then now these particles can't be created, they can only be annihilated. So we start to see the density drop. And so we're seeing the density drop here until at some point where now those two particles can't even touch each other to annihilate, they can't find each other. And this is the relic density that we see today, right here. And notice that if you increase the cross section, you actually decrease the relic density. And the relic density that we measure today suggests weak scale cross sections. And lo and behold, we were hoping for weak scale cross sections at the due to high energy physics and the hierarchy problem. So we thought this would kill two birds with one stone. And this is the WIMP miracle. And this is really the reason why there's been such a huge focus on WIMPs for the past 35 years. So this focus has been in three different directions. We've looked for WIMP production at the LHC with protons and protons colliding together, kicking off dark matter to one side and then a bunch of jets and stuff to the other side with missing momentum studies. Then we've looked for via indirect detection, where we look for dark matter annihilating in space and producing two visible particles like photons that we can measure with a satellite like Fermi. And then finally, there's direct detection, where we have dark matter coming in, scattering off a xenon atom in LZ, and producing light and ionization that we can measure. So this last one, direct detection, is what I'll spend my entire talk on. And I think there's good reason for this, and that is that this is the WIMP sensitivity versus time. So this is the sensitivity of the experiment on the y-axis versus the 35 years that we've been doing direct detection for WIMPs. And what you see here is we've actually done 7 orders of magnitude of sensitivity improvement over 35 years. So I think this shows why this is such an exciting field and why this has been an exciting field actually for 35 years, is that we've done 7 orders of magnitude better. And in fact, since the xenon TPC era for the last decade, we've actually been improving at something like, times 10 every 3.3 years. So direct detection is clearly exciting. So, and it's actually still exciting. Here is LZ sensitivity. And you can see right here that there's a lot of exciting supersymmetric particle parameter space that'll be probed with LZ. But it is also true that for the past 35 years, we've been searching super successfully. Again, 7 orders of magnitude improvement in sensitivity of these searches over the past 35 years. And yet we actually still haven't seen WIMP dark matter. And so for the past 5 or so years, there has been a consensus in our community that we shouldn't put all our eggs in the WIMP basket. And we should really start searching and doing broad searches across lots of different mass scales. And this idea is really highlighted in this Cosmic Visions community paper, which I link at the bottom. So to think about some of the theoretical models of these at mass scales outside of the WIMP range, in particular in the range that my experiments focus on, which is 10 millieV to 10 GeV, we're just going to rethink about what are the possible constraints on dark matter. And the first one on the low mass side is just the perturbations in dark matter are galaxy size. So that sets a limit of 10 to the minus 22 eV. And then there's another constraint on the bottom side, which is only for fermionic dark matter. Fermions you can't pack because of the Fermi exclusion principle. So that means that the mass of fermionic dark matter must be something above 100 eV. And then finally, these things on the high side go up to the Planck scale, and then, particularly if you have aggregation after, during the universe, and you make dark atoms or some kind of fuzzy dark matter, or if you have black holes, you can go well beyond the Planck scale. So there really is a huge range where we could be looking. So let's think about production, particularly thermal production. So if we want to produce dark matter thermally, then that means it's going to start out like early and hot, right? So we need it to cool. And relativistic particles don't clump. And dark matter actually begins all of structure formation. So this means we need dark matter to be relatively cold. And that sets a limit on thermally generated dark matter. It must be greater than something like the few keV scale. So that's the lower limit for thermally generated dark matter. And now let's look at a few different theories that we're going to be probing. And the first one actually goes back to this idea of freeze out that we showed with the WIMP miracle. But now we're just going to replace WIMP with baryon. So we're going to replace WIMP with proton, and we're going to go through the story. So in the early universe, there's a bunch of protons and antiprotons, and they're in thermal equilibrium. They're being created and annihilated. And as the universe cools, we go down this curve and the density starts to decrease because they start to annihilate. And then as it expands, the cross section for proton antiproton annihilation is enormous. It's strong. It's the strong scale. And there it is. It's a strong scale. So that means that the relic density is going to be incredibly small. And this says that under this narrative, we don't exist. So what's wrong with this narrative? It's clear that there is the solution is that there's only protons around, and that there's an asymmetry in the number of protons and antiprotons in the early universe. It's a very tiny asymmetry, but that asymmetry is what we're made of. So after this, this annihilation, what's left is actually just this small asymmetry. And that's the protons that are in the sun. That's the protons that are made of you and I. So maybe the idea here is that maybe dark matter is also asymmetric. And actually Lawrence Hall worked and wrote some papers on this concept back in 1987. So another option is the strongly interacting massive particle. So here, rather than using two dark matter annihilation, where two dark matter particles come together and annihilate, here we have a 3-2 annihilation system where 3 dark matter particles come together and they annihilate to get and producing 2 dark matter particles. So the thing about this annihilation diagram is that it requires 3 particles to get very close together. And that's very unlikely. And so what that means you have to really boost up the cross section for this dark matter interaction to huge levels. And that's why this is strongly interacting massive particles. So now this is strongly interacting on the dark matter, the dark sector side. So that's totally allowed. It's not strongly interacting with us. It's still dark. But there's thermalization of the dark sector through some kind of portal to the visible sector, which then we can probe with scattering in the future. So a few comments here. Again, if you notice here, Lawrence Hall actually created this idea in 1992, but then it was like reinvigorated and sort of refound in 2014 by Yonit, and who was a Berkeley postdoc or grad student at the time. And then finally, Hitoshi started writing a bunch of papers on this idea. So this idea really has been centered in Berkeley. So the final one we have is freeze-in dark matter. And lo and behold, it's also, you can't see it because of the zoom bar. This was also proposed originally by Lawrence Hall. He was just a rock star for a few years, clearly. And what we have here is now with freeze-in, we have dark matter that is very, very feasibly coupled. So dark sector has a very, very small coupling to the light sector. And that means the light sector is thermal, it's creating annihilating particles, but it only creates a very few number. The rate of production of dark matter is very, very small. And so that means it's never in thermal equilibrium, but it's just slowly increasing the dark matter density until the universe cools below the mass of the dark matter. And then that's your relic density. So the problem with this is that the couplings are so small that it's actually difficult to see with accelerators and indirect detection. But actually, it's okay for scattering, for direct detection, because you can go into the low momentum transfer limit, and the scattering rates go as 1/q². So this is something that actually direct detection has access to that pretty much no other dark matter experiments have the ability to probe. So the final theory that could be in this mass range is supercold bosons. Again, we talked about the thermally generated particles above something like the warm dark matter limit of a keV. So below this, the dark matter must be created ultra cold. It must be created basically at rest. And there's been lots of ideas of how to do this in the early universe, but they're all something like the misalignment mechanism. So for us, the particles that we're probing below something like a keV, axions and dark photons, would be made by some kind of ultra cold generation mechanism. So I think those are 4 theories of how to generate dark matter in the early universe. There's definitely a few more that you can see in the community white paper, which I've giving you the archive number 4 on the bottom right. But this means that I think this area is viable and must be probed. So let's go back now and think about WIMP design drivers here for a bit. This is high mass WIMP dark matter, and think about what are the dominant design drivers for the system? And the first is backgrounds. So if we look at how here's a nucleus, dark matter is coming in, scattering off the nucleus, we see that the recoil scale is something like 10 keV. So a 10 keV energy scale is exactly the same as the energy scale of radiogenics, of particles being thrown off by uranium and thorium and all of their chains. And so this means that we're sort of looking for a needle in a haystack. And the first design driver for WIMPs is minimize radiogenic backgrounds. So, and how do we do this? We get rid of the hay, right? So we go underground, so we're shielding cosmic rays with the Earth. The Lux detector and LZ is 4850 feet below ground at Homestake. And then secondly, we only use radio pure materials and fabrication techniques. So the next thing to make them even that's not enough to get rid of the backgrounds. So the next thing we do is we say, well, we like to scatter dark matter off of the nucleus because of coherent rate enhancement of scattering off of all the nuclei together at the same, all the nucleons together at the same time. And by contrast, the backgrounds, these photons that can get through our shielding, they all want to interact with the electrons. So if we can somehow have electron recoil versus nuclear recoil discrimination, we can again separate those two backgrounds. And that's the next thing that we do. So that's all how the dominant design driver for LZ and for WIMPs. So the next design driver for WIMPs and for all dark matter above 10 GeV is just exposure. So what we measure in our galaxy is the dark matter mass density. So the number density is a mass density just divided by the hypothetical mass of the particle. And that means that the interaction rate, which scales as a number density, we have the interaction rate we want, which is hopefully just really small, not really, really small, is the cross section, which is small, it's dark after all. The number density, which is small, if it's a very massive particle. The velocity is 1 e to the minus 3, it's small. So to make this really small, the size of the detector must be enormous, the number of particles in the detector. And so that's the second design driver. You need a really big exposure to do WIMP searches. And this is what we see with LZ. So LZ uses xenon. And why? It's a high Z material that self-shields external backgrounds. So secondly, it's a noble gas. So it's very easy to purify and make ultra clean. So it doesn't have any radio impurities in it, or very, very few. Then finally, we have a big exposure. LZ is 7 tons. And it's relatively easy in terms of 7-ton experiments to do, right? It's not like 7 tons of, I don't know, making a crystal experiment. And so this is why we actually have such amazing sensitivity increase with time, is that throughout this entire 35-year history, we've been constantly pushing on these design drivers. And the ultimate expression of that is LZ. So I think what this means is now we should do the exact same idea of if we want to have that same exponential sensitivity improvement in light mass dark matter, what we really want to do is we want to understand the design drivers of the system. So what are the design drivers? Well, here is right now basically the sensitivity curves for dark matter nucleon interactions versus mass. And you see that all of the experiments just basically cut off and there's no limits down here. So why is that the case? And it's just two-body elastic scattering. So, we like to use big nuclei because of coherent rate enhancement. But then what that is like is that means then the dark matter is much less than the mass of nuclei, and that's like throwing an elastic ball versus the ground, right? Virtually all the kinetic energy stays with the ball. Very little kinetic energy is transferred to the floor or to the wall. So, and in fact, the transfer scales as mass squared of the dark matter. So this is the curve you have. So this is the characteristic recoil energy on the y-axis. And this is the mass of the dark matter on the x-axis. And you see this m squared scaling right here, right? And so let's look down here. So we're talking about at MeV, if you want to be sensitive to MeV dark matter, this suggests milli-eV scale energy thresholds for your detector. So no matter what, I think the idea is that the #1 design driver for light mass dark matter searches is energy sensitivity. That's just a thing that you have to always put in the front. So the second comment I want to make is that these numbers are really, really small. And if you think about what the electronic band gap in silicon is, it's 1.4 eV. If you think about the Frenkel defect dislocation energy in silicon, it's around 15 eV. So this suggests that nuclear recoils won't even produce any ionization below something like, for dark matter, below something like 200 MeV or so. So we don't expect any ionization from dark matter with masses of less than 200 MeV. Okay, and if you think about that, the vast majority of detectors we make are ionization detectors. So this means we need to use special detectors if we want to see nuclear recoils below, or no, from dark matter with less than 200 MeV of mass. So one final comment is on exposure. So that's the bad side. We have to make detectors that are enormous, like incredibly sensitive. So let's think about the good side. The good side is the other side of the coin in terms of the rates. So if we go to very light mass dark matter, the mass is much smaller. The number density then is much higher. And so the interaction rate scales as 1 over mass dark matter. So, LZ needs 10 tons to get to 10 to the minus 47. We need 10 kilograms to get to 10 to the minus 47 at 100 MeV. So this is amazingly powerful in terms of taking an experiment that takes an enormous number of resources and takes a huge number of people at LBL and across the country, and it allows us to turn it into a tabletop experiment for light mass WEMP. So light mass dark matter searches are tabletop. So the second thing was the second design driver for LZ was radiogenic backgrounds, right? So let's look at that. Those radiogenic backgrounds, they're basically on the scale of 100 keV or so in terms of their comptons. And so they're relatively flat. And so here I'm showing what kind of radiogenic backgrounds we can achieve in a good cryostat underground. And it's something like 0.1 events per keV per kilogram day. And here in colors, going from orange to blue, I have different dark matter masses and the spectrum of energies they would produce. And you see the characteristic energy scale goes down, but most importantly is that the overlap with this flat background decreases. So again, the second design driver for LZ, which was radiogenic backgrounds, isn't really a problem here. As I go to lighter and lighter masses, I have less overlap with that background. It doesn't overlap with my signal I'm looking for. So this is a huge advantage. We don't need to do any R&D on better, like great materials. We don't have to use only xenon. We have a wide variety of materials we can use that, they may be a little bit radioactive if you're talking to a WIMP search experimentalist, but for us, they're fine because the overlap is really small. Okay, so still we have this problem of milli-eV thresholds and micro-eV thresholds. So let's see how we can improve that. So the first paper going down this path, where we're looking for different dark matter signatures, was done by Reuven Essig, Jeremy Mardon, and Tomer Volansky. Jeremy was a grad student here at Berkeley to keep the theme going. I believe Tomer Volansky was on sabbatical here when they wrote this paper. So Berkeley has been at the core of this light matter, dark matter shift for the last 10 years. And the idea here is the problem with elastic two-body collisions is you have to conserve form momentum. And if we transition over to a three-body collision, where we have dark matter coming in and scattering off an atom, and then on the output is an electron flies off and a nucleus, we can sink a huge amount of momentum into the nucleus. And therefore, we can harvest a huge amount of kinetic energy. And we can pull all the kinetic energy of that interaction. So that's sort of the philosophy of inelastic electron recoil signatures. So if we convert this over to condensed matter systems, the idea is we're just going to use the lattice as a phonon sink, as a momentum sink. And we're going to look at an excitation of an electron from the conduction band to the valence band. So what kind of momentum and energy transfer do we have? Well, the momentum scale for a lattice is set by the distance between atoms. So that's something like, 4.5 angstroms, or in momentum units, that's something like 3 keV. Okay. And the energy scale for that excitation is 1 eV. So that's a 1 eV, 3 keV excitation, give or take. So notice what that is. So for dark matter, here is the dispersion relation right here. Right there. We have 1/2 mv squared, or 1/2 vp. V is 1 e to the minus 3. So you can just say for a 1 eV excitation, we have something like 2 keV of momentum transfer. And what that places us is that says that the crystal momentum transfer for semiconductors, for indirect gap semiconductors, perfectly matches the MEV dark matter scale. So it's a beautiful system to match for momentum transfer to. So let's look at a few qualitative parts just to get a feel for inelastic electronic recoil dark matter signatures. So as I change the band gap, as here I'm going from helium to argon to xenon to germanium, germanium is way more sensitive. So what we see is that the smaller the excitation energies, the smaller the momentum transfer, your rate goes up sizably. So you really want low bandgap materials. You want semiconductors to do this. So secondly, the sensitivity depends on threshold. Again, for the same reason, it's all about momentum transfer. And so the lower the threshold, you can do exactly 1 electron hole pair, and you're sensitive to 1 electron hole pair. Then you can transfer the least amount of momentum, and you have the maximum rate. So what you need here is a single electron hole pair detector. So I want to make one comment, which is the downside to going to this inelastic electron recoil dark matter search technique is you have a lot more energy. But on the other hand, you've certainly lost some rate. So here are the curves shown here, right there, for electron recoil dark matter going across all these. This is for 1 kilogram year. These are those curves. And down here, down here, the bottom right, are curves for nuclear recoils. So this is for a heavy dark photon mediator. And so you see that you have quantum, you have a coherent rate enhancement because of the Q squared. You're scattering off of all of the charges in the atom. On top of that, you have a reduced mass dependence, which benefits you. So you get a huge improvement in sensitivity as long as you can see those very small recoils. So that's the price you pay when you switch to inelastic electron recoil dark matter. Here in my first few years at Berkeley, one of the things we wanted to do is we wanted to replicate these ideas of inelastic electron recoil dark matter and try to go below the semiconductor energy scale. So we could probe dark matter from MEV to the warm dark matter limit. And so here is some experiments that I did with, some papers that I did with Catherine Zurich and her collaborators, Simon, who is now a theorist at LBL. And the basic idea here is there was something wrong with the m squared dependence that I showed you in the previous slide for 2-body elastic nuclear recoils. And that is that we don't really have 2 bodies in a crystal, right? We have one body that's actually attached to the bodies, to the atoms next to it. So as soon as we get into the energy and momentum scales of the crystal lattice itself, which the momentum scales we've just been talking about, they're 2 keV. The energy scales are, again, something like the energy scale of the vibrations of the phonons, so 100 millieV scale. Then we can't think about that atom as being by itself and having 2-body elastic scatter. We instead have to think about dark matter scattering off of the entire crystal and producing a vibration. So we really have to change the ideas of how we look at dark matter scattering. So the first thing we can do is we can think about it scattering and producing an acoustic phonon. So those are these phonons down here. They have a linear dispersion relation. And that linear dispersion relation ends up changing the dark matter, the kinematics of the dark matter scatter. And it just makes it proportional to the mass of the dark matter times by the sound, the speed of sound of the phonon. So it's not now m squared, it's m. So it's gonna, it decreases much more gently with mass, which is great. Like that should allow us to go all the way down to keV. And the second thing is, it tells us exactly what we want to do. We want to use, if we want to look for acoustic phonon production, we want to use high sound speed crystals. We want to use diamond. We want to use silica. So here you sort of see what really this plot looks like in terms of the characteristic energy scale. Here we have single acoustic phonon production up to something like an MeV with hard scattering. And then we have here only soft scattering above that because there's a maximum momentum for single phonons. Of course, in reality, these two curves sort of bend together because we can go in between the two limits with 2 phonon production, 3 phonon production, etc. So here are some phonon sensitivity curves for 1 kilogram year of exposure with different energy thresholds. And really what I want for a nucleon cross section. And what I really want you to see is just this idea that there is, something like 7 orders of parameter space that are completely unexplored. And all one needs is just a detector that has single phonon sensitivity. Okay, so now let's talk about optical phonons. So acoustic phonons are those that, of course, you hear. And the idea is that in the unit cell, so let's talk about, gallium arsenide or sodium chloride, those 2 atoms are going to be going up and down together. So an optical phonon is one in which those 2 atoms go against each other and they're anti-correlated. So if you just think about the center, the total momentum of these 2 atoms, it's always 0. It's going like this. And that means that there's energy in this mode, but no momentum. So this is a gapped mode. So here's a dispersion relation for sapphire. And you see all of these optical phonon modes. Sapphire is an incredibly complex unit cell. There's something like 10 atoms in a unit cell. And so you have an enormous number of optical phonon modes that are all gapped. So what this means is because of their gap nature, you can kinematically match to infrared and light mass dark matter very easily. So here dark matter is coming in with this energy and momentum, and then it shoots off, gives off a phonon, and it kicks down to here. So you can see already the form momentum matching because of optical phonons. So even better, if you use a polar crystal, think about what this optical phonon mode is. So here I've shown you one of the high energy optical phonon modes at sapphire. And you have the aluminums moving in one direction, and you see the oxygens moving in the other, the red oxygens moving in the other direction. And this is a polar crystal. So what you're really doing here is you're changing the length of the dipole. And so you have a changing electric dipole, you're producing radiation. So what you see is you have very strong coupling of optical phonons in polar crystals to photons. And this is why, sapphire looks clear in the optical bandwidth, in the optical band, but at each of those optical frequencies, sapphire is completely black. And this is going to make it incredibly nice to search for dark photon coupled dark matter. And here you see some curves right here, these lower curves. That again, if you have sensitivities to a single optical phonon, you have 6 or 7 orders of magnitude of completely unexplored parameter space. So you can do the same trick with absorption, where now you're looking for lighter mass dark matter, below 3 keV. And here you're just absorbing all of the dark matter's rest mass energy into the optical photon, into the optical phonon. And you can actually see the sensitivity here. You see actually all of the little nodes in sapphire and then in gallium arsenide. So you also have very nice dark matter absorption capabilities. So the final thing, which I won't talk about that much, is the optical IR haloscope, which is another way to match momentum and energy and to pull out the energy of the dark photon and convert it into a photon, or the axion into a photon. And here you're using a metacrystal, a dielectric stack of different index of the refractions to help you with that full momentum matching. And again, this is a nice system which allows you to look for both axions and dark photon, dark matter below 3 keV. And the constraint here is you need a photodetector which has single photon sensitivity in the far IR. Okay, so here is my group here at Berkeley. Bernard is still pretty active. He's a professor at the graduate school now. He lives in Hawaii, but he still works. And he is really taking the lead on super CDMS management activities right now. But eventually he hopes to start getting in the lab again. And then clearly everyone else here are the people who really are going to do all the work I present in the rest of this talk. So the first experiments I want to talk about is my collaboration Super CDMS. And so this is on the higher mass scale. It's 500 MeV to 6 GeV is the dark matter it's looking for with nuclear recoils. And because the mass scale is so high, it's expected that these recoils produce some ionization. And this allows us to use very large crystals, so something like 1.4 kilogram in size, because there's ionization. And we can still get good energy resolution because we're going to use this Luke Neganoff gain trick. The Luke here, he was a research scientist at LBL for many years, and he proposed this sometime, I believe, in the 80s. And the idea is here is as follows. I have a semiconductor, and I have dark matter coming in. It interacts and scatters, producing some electron hole pairs, as well as some initial recoil phonons. Now, the electron hole pairs get drifted across a voltage drop. And all of that voltage, electrostatic potential energy, gets converted into phonons, into phonon energy. And therefore, the total phonon energy produced is not actually just the recoil energy. It's all of that electrostatic potential energy of those electron hole pairs. And so if you boost up the voltage, you then boost up the amplification, and you can turn your calorimeter into basically a single ionization detector with an with basically an ionization amplifier. So in my first few years here at Berkeley, we were able to see a single electron hole sensitivity for the first time. So here's photons coming in. Here's a Poissonian bunch, 0, 1, 2, 3, 4, 5 photons. Here, of course, if you can do that, you're going to do a dark matter limit immediately. So here is our first world-leading dark matter search with me as a faculty member here. It's this line here shown in red for electron recoil dark matter. And here I'm showing the light mediator limit. So the good part is, of course, it's world leading. The bad part is it's 4 orders of magnitude from probing Lorenz's Friesen theory. So we need to improve this by 4 orders of magnitude. Again, you see the same thing with the freeze out models. We're something like 4 orders of magnitude above where we need to be. So let's look at the background. Let's look at the events that we got in this search. And you see they're very, very quantized. You can actually see in the dark matter spectrum, you can see the signal. You can see 1, 2, 3, 4, 5 peaks, and you can even see the size. This is an enormous dark count rate of something like 1.7 hertz per gram. Okay, so this is way bigger than those radiogenic backgrounds that we were talking about earlier, which were, on the order of 1 event per keV per kilogram day. So what this says is that the second design driver we've now found for light mass dark matter, and that's we have to get rid of these low energy detector events, these detector dark counts. So let's look a little bit more into what these could be for super CDMS. So here's the super CDMS detector with loop Negative gain. Here are two hypotheses that we're going to think at critically. The first is, here is actually the picture. Here's a picture of this detector with the holder, and the holder is all insulating FR4 board. It's a PC board holder to hold that detector in place. So what happens if a high energy phonon comes in, scatters in the SERLEX, and in that scattering, you produce a bunch of Cherenkov radiation, you produce a bunch of scintillation light that goes flying around your optical cavity, and then gets absorbed by your detector. So here, two of those photons get absorbed by the detector, make electron hole pairs, and give you a 2 electron hole pair event. So this is one option. The second option is over here, and it's impact ionization at the surfaces. So here we have a tunneling from one of the bias electrodes. An electron tunnels off the bias electrode, flies across the crystal, then impact ionizes on the top surface, producing a hole that flies back down. So those are two possible hypotheses that match this idea of a quantized background. So we can actually just very quickly, we can actually figure out which of those hypotheses match the data. And the impact ionization hypothesis doesn't match. And I can show you why here. So if you think about those events, those impact ionization events occurring, their probabilities should be independent on the two sides. So the odds of me having an electron impact ionize and produce a hole on one side should be completely independent of what happens on the other side. So that independence should be seen here as a constant factor between the peaks. And what we see in the red is we see that constant factor of something like a factor of 4 for the 2, 3, 4, and 4 peaks. But look at the 1 to 2 peak. We see a huge difference. It's over 150. And so this tells us that it's really, really hard to get internal dynamics like impact ionization to produce the spectrum that we see. And so this led us down the path that what we are seeing is indeed the high energy photons interacting with the SERLEX. And recently we've had 2 ways to test this and prove that this is actually what was occurring. The first is that we actually put 2 detectors right next to each other and we look for coincidences, and we saw a large fraction of coincidences. So where we saw a single on one, where we saw a single photon and a single photon event on both detectors together, which clearly shows that they're from an external source. So the second thing, which I'll say, is that actually Reuven Essig at the time was actually writing a paper independent of us, and he proposed that Cherenkov processes could actually produce the rate at roughly what we saw. And so he actually matched our feelings that that was our background. So what are we doing in my group to get rid of this background? Well, in my group, what we're doing is we're replacing all of this FR4 board of our structural and the structural support for the detector with nothing. So here is a detector that we're testing, which is just resting on bare copper. So the idea is that we're going to get rid of all of the insulators that are producing that Cherenkov photon, all non-instrumented insulators that are in the optical cavity. So you suppress that by 10 to the 4, then you go underground, which suppresses the number of events hitting the SERLEX or whatever that insulator, non-instrumented insulator is in the first place, by another factor of 10 to the 5, because that's the factor of background rejection just by going underground that you can get in a good cryostat, and you're at 10 to the 9. So this here is how I feel we're keeping track of our design drivers again, right? So just like LZ, how are they able, and high mass WIM searchers, how are they able to stay on this huge progress of 35 years, 7 decades? They were just singly focused on those design drivers. And here you see that we're doing the same, right? We hope to get that same exponential increase of every 5 years, 3 or 4 decades of improvement. And the way we can do it is here, right? This is a 10 to the 9, hopefully a 10 to the 9 decrease in our dominant background. And hopefully this will occur sometime in the next year. So I do want to now switch over to some of my more recent work that really dominates my lab. And I think we want to ask these questions. What if we don't want sensitivity not only to inelastic electron recoil dark matter searches and inelastic electron recoils, but we also want to look for nuclear recoils that don't ionize. And you saw there's huge advantages to doing that. What if we can't suppress that dark count rate? You know, I showed you what the dominant dark count rate is now, but that certainly doesn't mean that's going to be the dominant dark count rate in 3 years' time. There could be another background that's underneath there that we don't know. And so I think both of these suggest that we should build detectors with the idea of sensitivity to single phonons and single IR photons and single electron hole pairs without the use of external E fields, without the use of Luke Neganoff gain, which then could bring about all of these, all this charge leakage. So we want to run 0-volt detectors, which hopefully have fewer dark count problems. So for this work, my group really has partnered with a very strong group at LBL, as well as Dan McKinsey's group here. So the first experiment that we just started, it received funding by the DOE in June of 2020, was SPICE, and SPICE stands for Sub-EB Polar Interacting Cryogenic Experiment. And this is really based on those papers that we wrote, which were thinking about coherent excitations of dark matter interaction in polar crystals. And so here you actually see one of the first prototype sensors that we have of this. This is not vaporware. This is ongoing in a super active experiment. Let's see, of course, the exposure here is, it's not 7 tons. As we were discussing, it's something like 10 gram years is what we're hoping to maybe a kilogram year for this experiment. The energy scales are, we can search for nuclear recoils. And then secondly, we really want in the ultimate late reach to look for these optical phonons, which are in the 60 to 150 millieV range for silicon and sapphire. Okay, so there's a second SPICE experiment that was funded, which is gallium arsenide. And so here, the idea is we're going to look for inelastic electron recoils. And so dark matter comes in, produces an electron. That electron in gallium arsenide is a direct bandgap semiconductor. It has very high scintillation yield at low temperatures. It's been measured to be something like 60% quantum efficiency. And so a photon is produced. That photon then bounces around and is absorbed in a germanium detector up here on the top. And that signal is the inelastic electron recoil dark matter signal. So the perk of doing this over something like super CDMS HVEV, where you're drifting that charge, is again, there's 0 charge leakage. And secondly, we have a 2-signal coincidence in these 2 crystals. So we actually measure a coincidence, which we can use to suppress lots of potential backgrounds. So the idea here is really to be complementary to super CDMS HVEV. If super CDMS HVEV, has no backgrounds, it's clearly going to be the dominant experiment. If we still see backgrounds, this is our hedge. Our hedge is to look for these, look for ERDM with this system, where we have all of these extra additional background controls that we've built in. So the final experiment with an enormous number of background controls is HERALD. And this is actually an idea of Dan McKinsey and his group. You can see the original paper here. It was funded together with SPICE actually by the DOE. And it shares all the same aethermal photon sensor technology and electronics. And in that sense, hopefully it's cheap to do all these experiments together. But the idea here is, again, to look for nuclear recoils off of helium. And the thing I want to say is there's an enormous number of different channels here. So for example, a nuclear recoil, because so here dark matter comes in, it interacts with the helium produces a bunch of phonons and rotons. Those phonons and rotons bounce around, and eventually they end up here at this liquid vacuum interface. And these high energy rotons can kick off a helium atom on that surface. Be absorbed on these photosensors that are made of silicon on the top here, and that's our measure of the helium. So the hope would be it would be not just one pixel would fire, but we get multiple pixels firing for an event in the helium. And that would again give us this very nice coincidence signal that we can use to suppress all sorts of backgrounds that are seen on a single individual pixel. And here again, you see the energy thresholds for this detector. They're somewhat daunting, but we're going to talk about how to achieve them in the next few slides. So those are the new experiments we're doing. So now let's think about how do we achieve this single phonon sensitivity in massive calorimeters. So the first thing I want to think about is, let's say we want to look for a 100 millieV event. We have to recognize how small a 100 millieV event is, and that's that at room temperature, this table has something like 26 millieV of energy per degree of freedom. So every atom has 3 kinetic degrees of freedom, so that's on average 75 millieV of energy. Basically, the energy we're looking for is the kinetic energy of one atom in that table. And we're using relatively massive detectors. So we have 10 to the 18. So this straight off tells you that one cannot search for 100 millieV scale recoils with a room temperature detector. And so we're going to have to use some kind of superconducting sensor technology, either transition head sensors, MKIDs, superconducting nanowires, quantum capacitors, qubits, something of that ilk we're going to have to use to look for these small excitations. So we're going to focus on transition head sensors, which is something like probably a third of my group's effort right now. And a transition head sensor is just basically the world's simplest calorimeter. We have a metal film that is basically a heat capacitor, a heat capacity. Energy is deposited in that film. Its resistance heats up. Now, this is a superconductor, and we've purposely biased this superconductor in the middle of its transition. So a small change in energy in temperature gives it a huge change in resistance, and that's what we measure out. So the nice thing is you can already, just with undergrad StatMech, write down the expectation for the change in energy of a heat capacity connected to a bath. And I'm not going to go through the derivation. So here we have thermal fluctuations going back and forth between the bath through this thermal conductance G. I'm not going to go through it, but the average variance of the energy in that capacitor, in that heat capacitance, is C times kBT squared. Okay. So this is basically the order of the intrinsic noise of a thermal calorimeter. So there's some bandwidth. So order 10 changes on this number, but this is to first order close to what we should expect. So this tells us that if we want to do single phonon sensitive TSs, we're going to have to minimize the heat capacity, minimize the T, because it goes as C times kBT squared. And now the heat capacity scales as the volume. So, and times by the temperature. So the heat capacity of a metal scales as T. So that means that we expect the energy variance to scale as VT cubed. Okay, so this says that we have to minimize the temperature of this superconductor. We want to go as low as we can, something like 10 to 20 millik. We'd like it to be above your average dill fridge can do, I don't know, has a base temperature in today's world of 5 to 10 millik. So 1.5 that is the lowest we can go, but we want to go to that edge. Secondly, we want to minimize the volume, the heat capacity. So we want to use the smallest TS we can. So the problem is we want a kilogram of this stuff, or we at least want a gram of this stuff. And if you use a small TS and you use that as your absorber, you end up with really small numbers. So if you want a 20 millieV baseline resolution and your TC is 20 millik, you end up with a volume of 275 microns by 275 microns by 40 nanometers for your film. And that's just 60 nanograms. So to get 1 gram of active target mass, you would need 15 million channels. So this idea of just brute reading out 15 million channels to get your 1 gram is probably not viable. I will say that this works completely for the optical haloscope when you're just collecting photons and you're not actually absorbing in the TS itself. So the second most simple calorimeter is shown here. And that's the TS is connected to an absorber. The absorber is an insulator, so it has very low heat capacity. And there's a problem with this idea. This idea has been going around since the mid-1990s. And the problem is we want to go to low T so we can lower our TS transition temperature and get really nice energy resolution. When we go to low temperature, we decouple the electronic system of the TS from the phonon system of the absorber. That's because this G, the thermal conductance between the two, scales as T to the fourth. So when we have a dark matter event, right there, when we have a dark matter event go into the absorber and produce a bunch of vibrations, those vibrations won't actually get into our TS to sense. They'll instead just dribble out into the housing. And so this has been the problem since the 1990s with this idea. And so the solution is to go to an athermal phonon sensor technology in which you don't allow those phonons to thermalize. Dark matter comes in, produces a bunch of phonons. Before they thermalize, those phonons are just bouncing around ballistically, and we absorb them in aluminum collection fins where they break the Cooper pair into quasi-particles, giving the quasi-particles their kinetic energy, their energy, and then those quasi-particles diffuse and drop their energy in a very small volume TS at the very center, which you see right there. So this is a collection and concentration scheme. There are efficiency losses in this, but this bypasses that G constraint that we had in the other designs. And so now I want to do a little bit of a question and answer here, and that is these are somewhat novel detectors. Like we're thinking of athermal phonon, detectors that sense athermal phonons, but these same concepts actually occur with any excitation detector. So what I want to ask the question is I have a scintillator. A scintillator with the PMT is one of the most standard excitation detectors we know. And I put this PMT on a small crystal and a big crystal, and I ask if these have the same energy, if these will have the same energy sensitivity. And the answer is they will if the lifetime of the athermal excitation, in this case photons, is actually really long. So if this photon isn't absorbed in the crystal itself and just bounces off of the sidewalls of this crystal, and this is why for a PMT, you may actually wrap it in Teflon because Teflon is very reflective, then you'll eventually absorb that photon in the PMT and read it out. So we've made ourselves independent of the size of the crystal. And we want to do something very, very similar. What we'd like to do is use a TS that has a very small volume because it makes it more sensitive, as we saw. And we want to allow that phonon to bounce around in this crystal many, many times. And eventually, after 200, 1,000 bounces, we want to absorb it. So this works only, very quickly, we'll talk about how this scales. So here is actually my athermal phonon sensitivity. So if I am going to, these are some simulations. So here is the thermal fluctuation noise. On the y-axis is my power in watts per hertz. And this flat line here, this is the thermal fluctuation noise of just random energy going back and forth across this thermal conductance. And then here is the roll-off, and this roll-off is proportional to just C over G. This is the exponential fall time for energy that randomly ends up here in the heat capacity. It'll flow back down with some characteristic time C over G. So these are the power curves, the noise curves I see. And if my signal is really, really slow, if my bandwidth of my signal is really small, because I'm allowing that signal to bounce around for many, many bounces, then what I can do is I can lower the TC of my detector. That lowers my bandwidth, but it also lowers my thermal fluctuation noise, which scales as 4 kBt squared G, are T to the 6. So if I match my TS to my signal bandwidth, then I can end up with TC cube scaling. So I don't have just T to the 3 halves scaling for my energy resolution. I actually have T cube scaling for my energy resolution, as long as whenever my bandwidth of my sensor matches my signal, then I just lower the coverage fraction of my detector further and let the phonon bounce for longer. So I can always stay on this ideal curve of scaling as TC cubed, as long as I can go to lower and lower coverage fractions of sensors. And so this gets down to the ultimate limit of playing this trick. And that is there's phonon thermalization on that surface. And there was a bunch of studies here done in the 80s on looking at the quality of that surface versus in silicon. And you can see the inelastic scattering probability. This is a thermalization probability of a phonon on that surface. And you could see that they got to, 10 to the minus 3 to 10 to the minus 2. We also see that ourselves in CDMS, we can do 0.1 to 1% of the crystal surface, at least in silicon and germanium. And we don't see significant down conversion on the surfaces. So that suggests that we can play this trick and stay on this TC cube scaling law for a long period of time. So let's now talk a little bit about how we're going to go about doing this. The first thing we're going to do is we're going to develop ultra-sensitive TSs. And the first thing we want to do is we have to just lower the TC of our superconducting transition edge films from 40 millik to 19 millik or to 15 millik. And then we have to test these structures. So here's an example of us playing this out. So this is something like factor of 2 better than what we published. But here, this is a TS that has, it's a 25 by 100 micron by 40 nanometer thick TS. It has a bias power of something like 22 femtowatts. So just to set the scale, the bias power is proportional to the thermal conductance. The thermal conductance is proportional to the noise. So you can say that basically this is a measure of the noise we have. And just to set the scale, this 22 femtowatts compared to your average CMB-TS, something like Adrian uses, which is around 2 femtowatts, sorry, 2 picowatts. So we're something like 40, 80 times smaller bias power, 80 times more sensitive than the TSs that Adrian uses right now. So it's a very low noise TS. Here is actually the noise performance versus our modeling. Again, the line in green here is our thermal fluctuation noise. And you can see that the noise we measure is something like 1.5 or 1.25 times the intrinsic noise. And the energy resolution of this device is 20 millieV. It's, let's say this is competitive and maybe slightly better than groups that make optical TSs in the world. So now let's think about if we start lowering the TC, what are some other devices we have? Well, we've just recently made a film that was 19 millik in TC, which it scales as TC cubed, but we have a problem. So the 200 by 800 film transitions and we get 3 femtowatts. The 100 by 400 film is not transitioning, it's normal. So what's happening is we have environmental power hitting that TS and heating it up above its transition, so it just stays normal forever. So it's not operable. So we have something like a femtowatt of DC environmental parasitic power hitting these TSs. And so that's the next thing that we have to get rid of. Here you can see actually the near-term future that we're working with to figure out how this power is getting onto our system. We we basically have an antenna which we put 800 megahertz signal that we amplitude modulate at 200 hertz. So we can see the amplitude modulation in our power in our signal band, and we can see where the radiation is getting into our system, and we can filter it. And so we're doing this work now, trying to improve our cryostat, and then also we're adding some copper powder filters that John Clark produced as another way to try to suppress this EMI that's limiting our performance. And if that happens, again, the hope is we'll be able to do 2 millieV sensitive TSs. in the near future. So finally, we fabricate sensors on the crystal. This work was done actually also with Yuri in collaboration. So here is a big device. It was originally designed for neutrino double beta decay, but we're using it here as a test bed for our setup. The noise is a little worse than expected, something like 1.5, but it still looks good. We've calibrated it, and we have something like 4 EV resolution. This is an amazing device for its size. No one else in the world can make a device that's 3 inches diameter and has 4 EV resolution. So of course, the first thing we do is we do a dark matter search. Again, this dark matter search is it's at the surface. It was a 22-hour dark matter run, and we ended up with the exclusion curve shown in red. So nearly world leading, even compared to dark matter searches that are below ground. So this is super promising. Here, I'll give you a teaser. Right now in my lab, we have culled a sapphire detector, which for SPICE. So we're testing our fabrication. And this detector looks great. It has 200 femtowatt bias power. And so we hope to have, sub EV sensitivity with a huge 3-inch device. So that's it. We'll skip a few slides. And the summary here is, I think there's viable and well-motivated dark matter models throughout this range of low mass dark matter between something like a GeV or 100 MeV and 10 millieV. And then the design drivers here are energy sensitivity and dark counts. And our current progress, we have produced photon detectors and run dark matter searches with 4 EV resolution, and hopefully perhaps a lot lower very soon. We have we have very small TS chips starting this idea of making ultra-sensitive TSs, which is the core of any kind of athermal photon sensor, of 20 millieV. And we have 19 millieV TS chips on the way, which hopefully will get us down to 2 millieV sensitivity. So I think the future is pretty exciting over the next 5 years for SPICE, Herald, and Super CDMS. So thanks.
So first we'll start with questions. Anybody have a question? Well, I'll ask you a couple of questions. One is, as you probably know, TES sensors are used in astronomy also. They hope to be used. And I'm just wondering, since you're getting greater sensitivity with your TSs than others, as I understand it, do these show potential for really having a big impact in astronomical?
Absolutely. I think they certainly could be used for example, far IR searches. Mm-hmm. So for searches for life, I think they're completely viable. I do think there are other superconducting detector technologies which are also pretty cool in that zone as well. Like, I don't know, superconducting nanowires have been proposed in that range, and they also have, or they're getting better and better far IR sensitivity, and they're very easy to pixelize into huge arrays. MKIDs also are not quite at our level, but they're also there. So I think there's actually 3 viable superconducting detector technologies for those very far IR searches. But certainly TSs are one of them. I mean, we're going to have millieV sensitive TSs soon.
Excellent. My second question was, at the beginning of your talk, you emphasized the rapid rate of progress for doing detection with, for the WIMPs.
Yep.
I mean, now that there's so much sensitivity, is that going to continue getting a factor of 10 every 3 years?
Oh, yeah.
Are we going to reach a fundamental limit?
No, so there's a fundamental limit there.
Repeat the question.
Oh, yes. Okay, so the question is going back to WIMPs, is there a fundamental limit on the scaling law? Can we continue to expect, a decade of sensitivity improvement every 3 years? And the answer is no. I think truthfully, this is one other reason why the community has started to broaden its approach to start looking at other dark matter areas. And I'll show you. Second. So you can actually see the limitation here. And so we keep on pressing down. And here, LZ, the projected reach of LZ is something like a factor of 10 above the. So there's really just a factor of 10 more before you're going to have this irreducible background. You're going to have to start background subtracting. So you're not going to scale as max of the exposure. You're going to scale as square root because you have to start background subtracting, and you're going to start slowing down. So yeah, that's unfortunately we see the end of the high mass low surface for one generation.
Okay, thank you. You want to check and see if there's any
Sure.
questions?
Are there any special contributions that you've undertook to mechanically isolate your detectors from vibrations stemming from your pulse tubes? Certainly, there's two things. We have an interesting fridge by Cryo Concepts, which actually tries to decouple the pulse tube from our fridge. But actually, right now, we're actually designing a two-stage mechanical decoupler to improve beyond that. And I can actually show some slides of actually, you can see this vibration when we turn on and off our fridge. In particular, when I talked about the where we're going to hold our detectors without any mechanical support structure that is non-insulating, that is insulating for super CDMS. And this also works for Spice Herald as well, we believe, where we're actually trying to get rid of microfracture events. And one of the problems we have with our current setup actually is in fact what you're alluding to. And so here is actually a really nice experiment we did. So this is of holding with minimal stress and with no insulating surfaces. And we literally just rested a detector on the surface of copper. So we're going to have no Cherenkov backgrounds, and also we've minimized the stress on our detector, which we hope will minimize other backgrounds that I didn't have time to talk about. And if we look at this, we actually see a huge number of noise events, particularly on these detectors that we don't hold at all. So if we don't hold this detector down, again, if you think about clamping, you have clamping force that keeps that detector from moving. So it keeps frictional rubbing from occurring to a large degree. And so when we start to go into these holding techniques where we're just resting a detector on the surface, we start to end up with much more vibrational sensitivity. And therefore, part of our work program, because we want to go down this path of resting detectors and not clamping them, we're going to have to improve our vibration decoupling significantly, and thus the double mass decoupler that should be going in the next 6 months. There was potentially another chat. No, there's not. Okay.
Okay, any other questions?
Okay.
No,
that's it.
that's it.
Yeah, that's it.
Okay, great. Well, let's thank Matt again.
Okay, thanks.
Huge applause you normally get.
No, it's okay.
Anyway, thank you very much, Matt. That
Oh.
was really quite impressive research.